Okay, welcome back. Here at the end of section 8.2, I'm going to talk a little bit about some of the tricks you can play to rewrite a rational function as a sum of separate rational functions, simpler rational functions. So you've done a lot of this in Calculus 2, and we did some of it earlier in the semester as well when we did partial fraction expansion. So these are just a few tricks here. In fact, a couple I've never really didn't even know had names, and I guess I would have thought of them before, or maybe used them here and there, but not in any kind of formal sense. So this was interesting for me as well. Again, we have a fraction, a rational function. The numerator has degree that is smaller than the denominator. So here the degree of p is less than the degree of q. So this first example, 8.2.4, is a pretty straightforward one. Linear in the top, quadratic in the bottom. It's really nice that the bottom factors into these two factors, s minus 1 and s minus 2. Now, if it happened to be written as the sum of two squares, we've already seen examples like that, and those had nice forms. But here we're going to try to write it as a over s minus 1 plus b over s minus 2, as you see at the very bottom of the page. And then each of those will just be shifts of the 1 over s function, so that will give us our exponentials. And they go through the standard, I'll go down a little bit here, the standard method of multiplying the a by s minus 2 and the b times s minus 1 to get a common denominator. And then you multiply that out, and you equate your numerators, which gives us this very top one. Get a system of two equations, two unknowns, and you can solve. A is, I guess, negative 5, b is equal to 8, and that gives us ultimately negative 5 e to the t and plus 8 e to the 2t, where we have these shifts by 1 and 2 respectively, which is why the exponents on e are 1 and 2. Then they have a second method of doing that called the Heaviside method. I'll come back and talk about that later. Let's skip over it for now. It's just really a shortcut for doing the algebra. You can see here they call it the Heaviside method. Theorem 8.2.2 explains this method. And it's fine. It's a little shortcut. I'll show you an example later. They're using that method here in the solution. I want to just remind you about partial fraction expansion. In those previous two examples, the factors in the denominator were all distinct. And just a reminder, when you have a repeated factor, like here in example 8.2.6, each of those repeated, the one that's repeated has to appear as a denominator both to the first power, second power, third power, however many you have. So that's why we have two denominators with an s plus 2. The first one is s plus 2, the second one is s plus 2, the quantity squared. In each case, though, the numerator is still a constant. We would not need to have a bs plus c or something like that. Just a constant over s plus 2 and another constant over s plus 2 squared. They note that the Heaviside method won't work really here because of the repeated factor. But instead, they get a common denominator, like I mentioned before, and multiply them all out. You get more variables, but the idea is still similar. Here's one where in 8.2.7 where the denominator is s plus 2 the quantity cubed. So this is an interesting approach. Here, again, just as before, we have three terms. So in our sum, denominators are s plus 2 raised to the first, second, and third power, respectively. And we could get a common denominator and multiply it all out, but the alternate approach here, which is interesting, is to try to write that numerator s squared minus 5s plus 7 and expand it out with s plus 2 as a factor, because that's what's in the denominator. We'll see how that works. So take this s squared minus 5s plus 7 up here and replace s in each case with s plus 2 minus 2. So you can see that here. with the s squared, and you see it again here with the 5 times s replaced with s plus 2 minus 2. And then you multiply all that out, and you get the s plus 2, the quantity squared, and that times is there. Twice the product would give you negative 4 times s plus 2, and then you get a plus 4, and you expand this one out, and so on. You collect all your terms, and I didn't do it, but trust them. That's what you end up with, s plus 2 squared minus 9 times s plus 2 plus 21. And you stick that over s plus 2 cubed, and then you write it as the sum of 3 rational functions. So it's really nice. The s plus 2 squared over s plus 2 cubed gives you 1 over s plus 2, and so on. Minus 9 over s plus 2 squared plus 21 over s plus 2 cubed. And you can look those up. Those are shifts, as we discussed it, by 2 in each case. That's where the e to the negative 2t comes from. And then the rest is the inverse Laplace transform of 1 over sort of the variable squared, the variable cubed, and so on. So we get a really nice shortcut, I think, for finding that one. Take a pause here. I'm going to get ready to show you an example with Heaviside. Okay, here's an example with another rational function, degree 2 on the top, degree 3 on the bottom. And so we can rewrite this as sum a over s plus 1 plus b over s plus 2 plus c over s minus 2. Alright, so I'm going to do this the normal, traditional way, and then we'll see how it leads into Heaviside. Heaviside's method is not anything mysterious or magical. Well, it seems kind of magical, but there's a reason for why it works. So we have these 3 separate ones, and if we did it the traditional way, then we would get equals a times s plus 2 times s minus 2 plus b times s plus 1 times s minus 2 plus c times the other denominators. And that's all over our common denominator of s plus 1 times s plus 2 times s minus 2. And on the left-hand side, we still have our f of s, which is also that same s plus 1 times s plus 2 times s minus 2. And the numerator is this 3 minus s plus 1 times s minus 2. So these are true should be valid for all values of s, and if the denominators are the same, we can ignore those, and we just set our numerators equal. Right? So we have this 3 minus s plus 1 times s minus 2 equals a times all that plus b times all that, c times all that. Right. So if we want to solve for a, we can leave that on the right-hand side. And on the left-hand side, we get 3 minus s plus 1 times s minus 2, and bring over the other ones, minus b times s plus 1 times s minus 2. Bring over the c times s plus 1 times s plus 2. And all that has to equal a times s plus 2 times s minus 2. But if we're solving for a, we will now divide by s plus 2 times s minus 2. And now think for a second about how you're going to most easily solve for a. Okay, I rewrote a little bit by splitting up the numerator into separate parts. Ooh, I left out one. Oh, sorry about that. I missed this term here. So we should also have a minus s plus 1 times s minus 2. The s minus 2's cancel. So I need this term right here. and that was going to go in there. Okay, so I had this term, this term, this term, and this term. I divided each one by this denominator, and in all cases, except the first case where we had the 3 alone, one of the term factors canceled out. And on the right-hand side, we have this equal to a. And the point is that this is true for all values of s. These are equal polynomials, while the right-hand side is a constant. So any value of s you stick in there, it should give us a valid equation. In particular, let's let s equal 1, because then a lot of these terms are 0. In fact, all of them are 0. That one's gone. Let s equal -1. Apologize, that s equals -1 so that we can get 0 in a lot of our numerators. So then this one is 0, this one is 0, that other one I added is 0, and all that we have when s equals -1 is 3 over -1 plus 2 times -1 minus 1 equals a. And that's -1, -2, so I guess we have 3 over -1 times -2 is 2. Right, so just like that, we found a. And if we go back and look back at our original, with the Heaviside method, what they say to do is, if you want to solve for a here, let me change my pen color to something more striking, that you ignore all the terms where, say, there's an s plus 1, so you're going to let s equal -1 to solve for a, so that this is gone. And you just ignore everything. So you're going to ignore that one, you're going to ignore this one, you're going to ignore this one, and now when we plug in -1, we get 3 minus -1 over -1 times -3, and that's going to give us 2 minus -1 is a 4 over -1 times -3 is 3. Let's see, that's not right. I'm going to have to go back and look at this method. Give me a second. You can look for it too. What did we do wrong? Okay, maybe you found my mistake as well. A couple things went wrong. Here in our denominator, we had -1 plus 2, which is a -1 times -2. So that should have been 3 over -2. Okay, so a equals -3/2 is what we're looking for. And when we go up there and use Heaviside's theorem, what I did wrong, the only place where we ignore the s equals negative is in the denominator, where -1 plus 1 would give us 0. We ignore this term. Everywhere else we have to plug it in. So we have 3 minus, this will be 0 times 0, well, it doesn't matter, but that will be -3. And we ignore it in the denominator here as well. It just happened that there was a s plus 1 factor in the numerator, and we wouldn't have to have that. So you just ignore it in the denominators. Plug -1 in here, and we get -1 plus 2 is +1. And here we get -1 minus 2 is -3. So we get a -1 times -3. Let's see if that's right. Can we take a second and look at that? All right, well, I had lots of errors. What we got here was right. We had 3 and -3, and if you take that quotient, 3 over -3 is -1. And we had a mistake down here at the bottom, too. I had copied this wrong. That should be an s minus 2, and when you plug that in, you do get a equals -1 as well. So the same calculations we used up above, we used down below. It all is similar right here, and that's Heaviside's method. You would use something similar to get B and C.